I'm Mike Lovegreen, and I'm with the Upper Susquehanna Coalition Stream Team. Now, previously, through our Emergency Stream Intervention Program, we've talked a little bit about how a stream functions, what are some of the things you can expect, and how we destabilize a stream. Today, we want to talk a little bit about how do we get to that ideal cross-section. How do we start to emulate something like this that's in a stable condition, has an expanded floodplain, and reacts very efficiently. So in the next couple of minutes, or 15, 20 minutes, whatever, we'll talk about stream sizing, and we'll talk about some classroom examples on how to apply this.
So now we're going to move into basically the meat of the program, channel sizing. Channel sizing, we're going to discuss how we have come up with a process in which to determine what size the channel needs to be when we get into an emergency situation to do some channel modifications or channel cleaning or channel maintenance. This section will show us how the process is going to work when we try to make decisions on what to do, where to do it, how to do it, and that sort of thing. So the first thing we need to know is bank flow. Basically, our channel sizing that we do using this emergency stream intervention program is based on what we call bank full. So bank full is the channel forming discharge. It's that discharge at which things start happening and material starts moving and the channel starts morphing itself to what it wants to be in order to move sediment through a reach and to change and move itself so that it can actually create a morphological channel. So the definition we have in this slide, the bank full stage, corresponds to that discharge rate at which the channel maintenance is most effective. That means that the channel is maintaining itself. The discharge at which it's moving sediment, forming or removing gravel bars, forming or changing meander bends and meanders, and generally doing the work that results in the average morphological characteristics of the channel. So this is the flow at which the stream is trying to stabilize itself to move that bank full discharge rate through it without creating erosion and without creating deposition, without creating head cutting or creating that sort of thing that's going to destroy the channel. So this is just the standard detail that's used trying to show what the bank full stage is. Of course, we have a stream channel which has the present flow, which is generally in the summertime lower than bank full stage. The present flow here is probably from the aquifer recharging that stream channel. The bank full stage is that stage where the stream just starts to come out of its channel and spread into its floodplains. And then that's the bank full stage. So the slide here with the blue line is trying to depict where bank full stage may be in this particular stream event. You can see where the cross-sectional area, the black line, is showing the active part of the channel down where the larger stones are, where this channel, this area here is very active and the stream is engaging it on a an average and probably a stream discharge at about 1.5 to 2-year storm event. Once it hits this area here, it's getting into the floodplain, and this is what we're calling the floodplain at bank full stage right here. This is where we'll start seeing some finer deposition of sediments, or this is where the debris ends up collecting Those are some of the indications. Vegetation can sometimes be an indicator of where bank full might be, although in our areas it's kind of tough to determine by vegetation. We're basically looking for that floodplain deposition area on tops of point bars or these floodplain areas here throughout this section. So here we are trying to determine where bank full elevation is within this stream channel. Mike's picked up a larger stone there, so we know that's part of the active channel. I'm looking for some indicators where there may be some fine granular material that's depositing, and the vegetation line there at the end of that survey rod is giving me the indication that's about where the channel is activating its floodplain. So we're going to take a tape measure and measure across the stream channel to get that bank full width measurement. And Mike's going to the opposite side of the channel. Basically, the other side is disturbed, so we can't find a good indicator over there. So we're trying to just shoot it level line, or keep the elevation the same on both sides, so that Chelsea can take the survey rod now and go out into the channel to see if we can come up with a bank full depth in that channel. There she goes. She's going out to measure the deepest part of that channel to give us a depth. And that gives us the depth. We can sometimes take these measurements and see how they match to the regional curves and see if we're somewhat close, or if they're way off, then we have to take another look, or look at another cross section. So the channel forming discharge, that's the effective discharge, and bank full basically have the same meaning. So if channel forming discharge terminology is used, that is the bank full stage. For an example, in Delaware County, the channel forming discharge is somewhere around the 1.5 year storm event. And that's probably true from the area that I am familiar with in Steuben County, New York. So knowing that the discharge rate, we have had regional curves. We've had regional curves designed to show what bank full depths should be, which will give us the depth of the channel. That's going to show us what the channel forming discharge height is generally. So we use these regional curves in order to decide what size the channel should be, what depth the channel should be, and what width that floodplain should be, in order to have a bank full discharge that's just moving sediments and not eroding and not head cutting or depositing material in the channel. So we can use an existing stable reach if we can find one on that stream that we are attempting to make a determination on what the bank full width should be and depth and all that. So tables may not be required. If we can find a relatively undamaged reach, we may use a cross section either upstream or downstream of that. So what we're looking for is an area within a riffle rather than a meander bend, in order to duplicate a cross-sectional area by drawing a sketch and surveying to figure out the bank full width, depth, floodplain width, the bottom width, meander curve radius, and the slope is what we're looking for. And of course, your soil and water district can assist you with these determinations if need be, or where to take the slide or take the cross section. Here's a photo showing some folks from Delaware County looking for a riffle section in order to take a survey in order to figure out the bank full width and the depth. And within a riffle, you can see they're taking they're taking the measurements within a riffle area rather than maybe down in here where there might be a pool area. It's a riffle. That's pretty important because if you get into where the pools are, the depth is going to be an issue when you're doing the survey, because you're going to find deeper areas in the pool that aren't going to be a riffle reach type cross section. They'll be different. So using an existing stable reach, we can either set up a level, or we can use we can stretch a tape. We just need to get some measurements to actually show where the thaw leg is in the channel, which is the deepest part of the channel. Maybe we can depict while we're out there surveying where we feel bank full flow may be. That's probably the most important section of the survey. That'll give us the survey will give us a channel bottom width that's existing, and it'll give us the size of the floodplains that exist there. So once we get all those measurements, then we can duplicate that in another section of the stream channel. So here's a slide showing basically some of the measurements we're looking for. So we're trying to survey where bottom width of the channel may be within that riffle. That's that yellow line. So it would be from the edge of flow to the edge of flow probably. The bank full depth is going to be where the deepest part of the channel is to where the bank full discharge occurs. So that bank full discharge in this slide, you can see where we're at about the top of a point bar here in this section. They probably started getting some smaller deposition in this area here, so that was an indicator that the bank full height may be in this area. And then we draw that same elevation across to the other side, where this channel here seems to be a little bit steeper. Most of our floodplain in this one looks like it's over on this area. So once we get our bank full width figured out and our bank full depth, we can then try to survey where our floodplain width would be. Meander radius and slope. So it's good to try to get a average slope of that channel, so that when we go back into configure a new channel, we're using the same slope of that channel and not increasing it or decreasing it. Because when we do the construction, if we make the slope too steep, we could create a head cut upstream, or if we make it too flat, then we're going to create that head cut in a deposition area. So we have to make sure we get a good slope reading. And the meander radius, of course, is the stable meander pattern, or the curvature of the stream that is occurring in a stable reach. So if we can mimic that, then that will reduce the erosion in the future on the opposite bank of a point bar. So based on a lot of USGS data, regional curves were developed for the entire New York State. Basically, they came up with regional curves based on the size of the drainage area. So regional curves are basically another way or means to get a channel dimension showing bank full and depth and width and floodplain width in order to configure a channel after a disaster. So basically, that represents the size and cross section of the natural streams in the region. So we have very many regions in New York State. So there are different maps or different charts based on the region that the stream is existing in New York. So the dimensions given again are the bank full dimensions, cross-sectional areas, bank full top width, and then the average depth, bank full depth on the charts. This is just a slide that is showing the data that had to be collected in order to do regional curves based on drainage areas, and a lot of data that had to be collected in order to determine the sizes of those channels on those regional curves. So generally speaking, after a flood, channel dimensions have often been changed. Either they're too big or they're too small, or there's just something different going on there, and we need to see how they fit the regional curve charts. If it's difficult to determine the original size of the stream, if you just can't find that stream reach either downstream or upstream of the area that we've had a damaged section, then these charts or these regional curves will give us a reasonable bank full dimension depth, width, floodplain width that we can use in order to construct the channel back. So proper width and depth are very important, especially for the hydraulics. They're sized to carry the bank full flow. So it's that bank full flow is very important. That's a very important determination to make in the field, what the bank full flow is and how to construct a channel back to bank full flow. Bank full flow is the size that we're looking for to properly move the sediment within that watershed through that reach without creating erosion or deposition. So we're trying to build a channel that is not going to create a head cut or cause deposition, which is going to could possibly give us an avulsion in the future. And it's better for the environment.
Jeff, if I might, I just wanted to jump in here.
No,
that,
please, Mike.
Yep.
Go ahead.
When we're looking at regional curves and utilizing them, we need to consider that those regional curves are just again a generalization, a model, and they're most valid for those riffle pool type situations. So different streams are going to have different configurations, as we've talked about in this presentation, different points of where they access a floodplain, and actually, some of those stream types, like that step pool situation, don't even have a very active floodplain. They just exist in that V-shaped valley. So again, those reference reaches are extremely valuable. You're trying to recreate something that is proper for that valley type and that setting in the watershed for that stream channel. So use regional curves with a little background information of what needs to sit in that section of watershed.
All right. So generally speaking, in a step pool system, you're better off trying to find a section of that stream to survey and get a typical cross section of to match it if you have to repair any damaged areas on a step pool system.
Yep.
Rather than using the regional curves.
Yeah, and you have historical data, so you should already know what type of stream that you're working in when you're doing the repairs.
Yeah. Excellent point. Thanks again, Mike.
Yep.
Deeper bank full channels support aquatic habitat much better than the dish pan construction that has been done in the past in many areas in the state. You need a water depth that is going to maintain the fisheries or the aquatic habitat, and we need to have that channel size so that it properly moves sediment and through the channel without creating deposition and or creating erosion. So we need to find the bank full channel dimensions. So the tables have been provided that suggest the construction dimensions in the manual that we have put together that complements this program. So what do we need to know? We need to know the drainage area, the size of the drainage area in square miles of the basin that we are located in. As you can see to the right hand of the slide, there's a delineated watershed right there, giving us the size of the drainage area that we're dealing with. We're looking at that total drainage area from the downstream, or where your issue or where your channel is that we're trying to size down in here. We need to know the entire watershed that comes to that point. So this is a delineated watershed on that slide. Then we need to find the bank full channel dimensions. So drainage areas, there were static maps designed for New York State, or they are being developed, or they have been developed. I haven't seen the static maps yet, but they are supposed to be available. There's also another program that we use called Stream Stats New York, and the website is here in blue of the program, computer program that we use quite often to determine the size of the drainage area that we're dealing with. And of course, if you can get into that website, you can, there's ways that you can run through the program that'll give you a step-by-step instructions on how to find your location on a map, and the program itself will actually run a drainage area for you and give you the drainage area in square miles. So the stream stats will provide us the regional curve data that we need, that we can use with the tables that have been generated, either through the static maps, or there are actual tables that we will use for those drainage areas within the state. Classroom examples. So is this where you were going to come in, Mike?
Yep, I guess I'm up, and just
was there any comments before?
Yeah,
that you have on that last on the last set of slides?
Yeah, I just like to reemphasize to folks that are watching that, boy, if you have a stable reference reach, upstream or downstream or near your work site, an example of a reach that went through a storm, and you want to get something that's closer to what exists in nature, that's the best thing to utilize rather than these tables. We've got these tables, and as you'll see in some of the maps that will show, those regions are fairly large, and there's lots of variance within the regions themselves. So the tables get you close. We're trying to get close to what nature does, and then nature will readjust that stream channel and hopefully make it more stable. But if you have something on the ground, boy, that's the way to go. And another comment on those static maps, the maps have been developed for all of New York State, and they're color coded so that if you're not real good at delineating or don't know how to get into stream stats, you can have a color-coded map that kind of gives you an indication of how big that watershed size is based on the color of the stream that's in there. And again, they're available based on topographic maps, USGS topographic maps, and they're available for all the counties in New York. So good sources of information. Okay. Well, let's take all the things that we've talked about and use some examples to see how you can apply this when you're out in the field. And again, we've geared this this whole section so that you're out there and you're pretty busy. You're running around. You've got an emergency because of the storm. You've got damage. You need to go out and do a lot of assessments, and you're trying to determine where to work and where not to work, as we will emphasize through this whole presentation. And so you need something that's quick and nasty, that helps you get that stream back to a functional form, as Jeff indicated, without over excavating, without just going in there willy-nilly and hogging out the stream, but again, getting it back to where it's going to do that transport of both sediment and water, and hopefully stabilize itself so that eventually you'll have, healthy habitat and all those other environmental benefits that we hope to gain. So example number one, Woodhull, New York, and you're working in the stream. You've got some repair that's needed on a small stretch of stream, and you've got a bridge about a quarter-mile downstream. So one of the nice things about that is that if there is a bridge, somebody actually did some design on that bridge, or hopefully did some design on that bridge. And they've probably got some information on how big that drainage area is that flows into that bridge. And since it's only a quarter-mile away, we can take that drainage area that they use to calculate the size of the span of that bridge, which is about 19.6 square miles. So knowing the drainage area, again, we didn't have to look anything up on maps or go to stream stats, but we know that drainage area from resources that we have available. We want to find, okay, how big should that stream channel be? What is that width at Bankful? What is that depth? What is that Bankful area? And how big should that floodplain be to relieve the pressure from that storm? Approximately 20 square miles for a drainage area. And we want to go to those tables, and this will be our first look at those tables that Jeff talked about. So here's that map of all the different regions in New York of where the tables were developed for. And again, those different regions reflect different climate, different topography, different soils. But again, I just want to reemphasize that they're only approximate for that region. So you're using a statistical model, you're using a model to get some dimensions, and they're going to be close. Hopefully they're close. Some of the experiences that we've heard that they might be a little bit too big, but again, nature will start to adjust that channel by moving in new sediment or removing a little bit and placing it in different spots. So you're kind of jump starting that whole process that nature is constantly involved in every time there's a bankful flow and that material gets redistributed. So we can see that Woodhull is actually located in the southern tier. So this region right in here, the southern tier region of New York. So we can then go to our tables, and here's those tables that are available to everyone. And again, you can see here, it's the southern tier region that we're looking for. And we know that we've got 20 square miles for a drainage area. So we go down through the drainage area table column here, and we see 20 miles, and we read across, and it gives us all the dimensions that we might need. So here we have that channel side slope that we want to do, and we use a 3:1 as kind of a go-to dimension because we don't want to make vertical slopes. We want to have stable slopes. Again, the stream will adjust that slope. That depth is about 2.4 feet, and again that top width, considering those side slopes of that channel, including the channel slope, is 7.4 feet. A cross section, that top width of nearly 60 feet, and a floodplain. We're looking to get a floodplain of about 130 feet. So there's all the dimensions for us. I mean, we don't need to go out and run calculators or anything else. We have nice, simple dimensions there. And for the answer to what we want to build for that reach, we have a bankful width, again, as I mentioned, of nearly 60 feet, a depth of 2.16 feet, and a bankful area of 127 or 128 feet, and a floodplain width of about 130 feet. So again, fairly straightforward, something that you can do on a sketch right there in the field and be able to present that if you need permits to the permitting agency, and give to your bulldozer operator, and he can go in there and construct that. And here's what that looks like, again, sketched out. Our example, there's our depth, and there's our bankful width. And so you add these numbers up and you get your bankful width of nearly 60 feet, and there's the floodplain width. So again, pretty straightforward. Example 2, okay, here we have some flooding in Andes, New York. And so we want to find, okay, we don't have a nice convenient bridge downstream. We want to figure out what that drainage area is and what we should be constructing for that channel. So first thing we do is, here's those maps that Jeff had indicated. So that map you can see is color coded, and the color for that section where our work site is in yellow. So we take that and we go back and we see that, okay, our drainage area is somewhere between 25 and 30 square miles. Now that's further upstream, so we're probably kind of default to that lower value rather than that higher value. So that map indicates that it's in yellow. The key tells us that it's between 25 and 30 square miles, as I just indicated. And since, again, it's near that upper end of that map, we're going to use about 25 square miles as a default value. So again, we go to our regional map and figure out, okay, where is Andes? And Andes is located in the Catskill West region. So we go to this Catskill West region. We pull up the appropriate tables for that. Again, as we did in the previous example, we've got 25 square miles. It gives us these construction dimensions. We go, we sketch that out, and it's as simple as that. So here we can see we've got a depth of 2.9 feet. We've got a total channel width of 52 feet. There's those 3-to-1 side slopes, which we know are 8.8 feet on both sides, and that gives us the balance for that bottom width. And then there's our floodplain width. So we can sketch that out, we can stake it out in the field, and then get the bulldozers running. So let's talk a little bit about work methods. How do we approach a project when we're out there in the field? Well, one of the things we want to do is not to remove the gravel so that material that has now accumulated there, we don't want to disconnect it from the floodplain. We really want to get back to connection to a floodplain. We want to be able to have that pressure relief valve so that when that stream starts to compress that energy in there from that moving water and all that bed load moving, we want it to be able to spill out onto a floodplain and relieve some of that energy rather than start to compress it or build it. We don't want to remove point bars. We talked about point bars earlier in the presentation. Some point bars are good. Some sidebars are good. You have to do that evaluation when you're in the field and based on the dimensions for what we want to look at. And if you're thinking it's too big, or you think you might have to start remove some of that material, don't be afraid to ask someone at the Soil and Water Conservation District or DEC or some other folks that you might have around that can help with that. So again, I've been on a lot of sites, and so has Jeff, where folks go, well, what are we going to do with all this gravel and all this material? We've got to truck that material out of there. Our experience is when you start to rebuild that channel connected to a floodplain, quite often we don't have enough material on site, and so you're scrounging for materials. So you don't want to over excavate. You don't want to take out too much of that material. If you need to take some material out, you may want to do your whole layout first to figure out whether you're going to need that material or not. And then when you do take material out of there, don't place it into the floodplain. Take it off site, utilize it some other place. But again, I think we've emphasized the value of those floodplains, and we don't want to put obstructions in those floodplains anywhere. Reconnecting a floodplain, again, those tables give you the dimensions of the floodplain. The elevation of that floodplain is at bankful. So again, you're starting your bankful cross section at the top of that floodplain. So if you need 130 feet of floodplain, you're going to construct that channel starting at that elevation where you have that maximum width of floodplain. You know, might not always get 130 feet if that's what it calls for, but you want to get as much as you can, because again, those floodplains are very critical to maintaining the stability of that channel. And then once you start at that floodplain elevation with reconstructing your channel or putting your channel back into that disturbed reach, you've automatically reconnected that channel to the floodplain. So again, that's why we start at that elevation. And again, as I mentioned, you know, make that floodplain as wide as you can to get close to those recommended widths. You know, when we look at the floodplain from a stream stability aspect, you know, that floodplain is sized so that specific stream can dissipate its energy across that floodplain. And the width of that floodplain is going to depend on the stream and again the hydrology of that stream. So, you know, that's where the tables, you know, really give us some guidance on that. And it's not necessarily connected to that designation of a 25-year or a 100-year recurrence or a 1% recurrence or a 10% recurrence or whatever it might be. It's really dependent upon the floodplain. It's needed again by that stream to dissipate its energy without causing erosion on that floodplain. A too narrow a floodplain will actually start to concentrate some water, and you might get some rills or even avulsions in that floodplain, and that's where some of them occur. So again, I just wanted to make that distinction in the different types of floodplains.
Yeah, so generally speaking, on that slide we had a while ago where it showed a 100-year floodplain and a 25-year floodplain and then bank full, is we're not talking about 25-year event floodplains or the 100-year event floodplain. We're talking about the floodplain that's needed at that bank full height so that channel can get out, spread out, and get its energy knocked out so it's not erosive. That's
Yep.
a good point, Mike, because
Yep. And that last bullet is the key one. Make it as wide as you can. It's better to have too big a floodplain than it is to have too narrow a floodplain. And as we saw in the Margaretville example, when you have too narrow a floodplain, boy, it's going to rip and tear like mad. But when you have a nice broad floodplain, it doesn't even impact on the grass.
exactly.
So, here's an example. We've got some structures in here, so we can't get that maximum floodplain, but we can get it on one side or the other. So, you don't necessarily have to construct that channel right in the center of the floodplain. You construct it where you can. You want to get all those elements that Jeff talked about, that sinuosity and that slope, to match, as close as you can to what should be there based on the valley that you're in and that area that you're in. So again, get the floodplain with where you can. And here's an example. Here's that site. They were only able to get floodplain on this one side, but when you take a look at what's there, it's starting to look fairly stable. Vegetation's coming in. That channel is right about where you put it to begin with. It's done some redistribution of some of that material. Like I said, once you get close to that cross section that you want and that configuration that you want, nature's going to take over and it's going to do some adjustment and it's going to fill in some of those holes. And here's that same site, later on in the year, and it's vegetated in and it's looking pretty healthy. It's the shades coming in, so that habitat and those ecological values that go along with those values of sediment transport are all functioning fairly well. Here's another example. This was some impacts on a dry brook stream in Arkville, New York. And again, you can see it's all ripped up and torn up. There's excess sediment was moving through the system, a lot of debris. And again, they were able to take a look at that and address that. And here's an aerial view of that same site. So here's the stream. Here was that original channel through here, but for some reason it got blocked up and it broke through here to join that receiving stream. One of the concerns here that made it a really high priority as opposed to, well, you know, a lesser priority is that right here is the town's water supply. So again, it was threatening that town's water supply, and so something had to be done to address this site. And here's that site, you know, after they were finished. So again, they were able to block this section off. They were able to reconstruct this original channel to those dimensions that are very stable, and things worked out fairly well. And we'll look at that site in a little bit more detail. When we look at root wads, a lot of times you have a lot of material on site. And if you have an avulsion, such as Jeff talked about, some of that woody material can be used to stabilize the stream bank temporarily, and until you can determine whether you need something a little bit more durable than root wads. But those, you know, debris trees that are conveniently located right there, you can use some of that below the channel grade, because again, wood starts to rot and deteriorate pretty quick when it's exposed to the air. But if you can bury it or get it below grade, so that again you don't have a lot of that rotting process going on, it'll last for a long time. And you know, if you're placing any of that material, remember that it is floatable. And if it does get exposed to a lot of those flows, it could be ripped out and wind up clogging up a bridge or culvert downstream. So you want to anchor them pretty much with large boulders and rocks. And here's some examples. And again, we don't want to turn you into design engineers, but you know, here's an example of using some old stumps or old trees, and you want to have those roots kind of exposed to those flows to deflect some of those flows off the banks, but you have some large rocks that are anchoring those tree stumps. I know my experience has been, you know, when I'm doing some kind of durable stabilization for banks, we tend to use a lot of rocks because their velocities are very high, and the energy is pretty high in a lot of our streams up here. So, you know, caution when you're using wood, when the flows aren't as significant as they are in most of our streams. Then they can provide a lot of habitat, and they can provide some stabilization. Or, you know, an appropriate use would be is if you have an avulsion and you need to block that avulsion to secure it until it becomes more stable in the future. That's a good use for wood. And here's an example in Arkville of using some of that wood. So you can see, you know, here's the main stream over to the top right of our picture. They're working off channel. So the avulsion went right through here where it went near that water supply for that town. And so they're putting in a kind of secondary stabilization or reinforcement in that channel that broke through there. They're burying these long stemmed trees. They're anchoring with some rock, and they're going to bury them. So here they are. Here's where it broke through to threaten that water supply. They've lined up all that woody debris that they had there. They're taking advantage of that in that channel that broke through. They're burying them below the grade of the water. And again, here's the stream way over to our left. They're burying that material below that stream elevation. They're putting some rock on top so that they don't become mobile when that water comes up again and starts to rip and tear. And they're going to bury all them. And here's the site after they're done. And you can see a little bit of the roots sticking out right here where they buried that. They did a nice job of fine grading that. And what they need to do is get some vegetation on there, whether it's planting some trees or putting some seed mix down there so that they get a quick cover to hold that really fine material in place. But here's an example of where the avulsion went to the right of our picture. It's now filled in, and we buried some of that wood to provide extra reinforcement to secure that bank. Vegetation, as I just mentioned, is extremely valuable. You know, that holds the stream bank together. You know, as again, when Jeff was talking about how the stream lays down its material, and it does that kind of, tiling of the material. That's all held together. And so after we've done construction, that material has all been loosened up, and so we have fines segregated from some of the larger stuff. And so that's, until that vegetation starts to come in, we have that threat of some of that erosion cutting some of that material away and washing it away. So we want to get vegetation on there just as quick as we can. And during emergency work, sometimes we don't have time to plant trees and shrubs right away, but we want to get back to the site as quick as we can. And even a quick ryegrass mixture or something for short-term stability until we get back is going to help hold that fine material together and keep it in place. So when we get those flows up again on top of that bank, it'll hold in place. And if you remember, when we talked about that flood emergency that they had down in Margaretville, remember that field, that recreational field just above where the buildings were, and not even the grass blades were moved because it had lots of broad floodplain to spread out on and drop that energy out of the system. So again, grass can do a whole lot to hold the system in place, and until we can get something a little bit more rugged in there, such as trees or shrubs. And again, if you need that woody vegetation, a lot of times DEC and the Soil and Water Conservation District, can help the local municipality get a vegetative plan in there. There are a lot of programs like Trees to Tribs and other programs where you can get a source of that woody vegetation and get some plants in there. So again, do that as quickly as possible.